In part 2 of section 3.4, we are going to discuss 3 super key ideas in calculus and also in physics: position, velocity, and acceleration. And we're going to explore how those 3 are related through graphs and through functions. For this first example, I would like you to just put your pencil down and put your listening ears on and just try to understand the main idea of what we're looking at here. We can see that we have what's called in AP Physics, and perhaps in your current physics class, a position time graph, meaning that it's giving the position of something over time. More often than not, this is a particle moving left or right on a linear scale or a linear table or something like that, meaning that it's only moving left or right, kind of along an x-axis. So this means that our position can be negative, 0, or positive. And we can see on this first graph here that at the start of whenever we measured this, the position of this particle was at -5 on the number line. And it remained at -5 here. There's our particle. It remained there for the first 5 seconds. So let's draw a little particle in yellow, and that's where our particle starts. For the first 5 seconds, 1, 2, 3, 4, 5, this particle doesn't move at all. We would say that its velocity during these 5 seconds is 0. Then at B, from B to C, these are just here to help us. From B to C, that particle does move. Over these next 6 seconds, from seconds 5 through 11, our particle moves at a constant rate from the position -5 up to the position 2. So over 6 seconds, it moves from -5 to 2, -2. What does that mean? The velocity, which is speed and direction together, the velocity is positive because our particle is moving from a negative number to one that is less negative. It's moving in the right direction. And a velocity is also a speed. So what is the particle's speed from B to C here? Well, it's just a line. So what we can do is just count rise over run. We can see what its speed is. It went from -5 to -2, so it increased by 3 units over 6 seconds. So if you're traveling 3 units in 6 seconds, that means you're traveling 1/2 unit per second. That's your velocity there. What does our particle do next? From seconds 11 until 20, from C to D, our particle remains stuck at the position -2. Its velocity is 0 because it is not moving. Then, at second 20 through second 30, so over the next 10 seconds, our particle moves from the position of -2 on the number line to the position of 8. So it moves here all the way to 8 over 10 seconds. So our particle just traveled 10 units in the right direction, I mean right as to the right, not as incorrect, over 10 seconds. Its velocity was 1 unit per second. Then, from E to F, over the next 10 seconds, our particle does not move. Its velocity is 0. Then, from F to G, our particle does move, but it moves backwards from position 8 on the number line to position 0 in a very short amount of time. That's really steep. That changes fast. So it goes 8 units back in 4 seconds. So our particle goes from 8 down to 0 quickly. Its velocity was, it moved 8 units in the negative direction in only 4 seconds. So its velocity was -2 units per second, since velocity is a speed and a direction together. So what did we just discover here? We just watched position change. And the rate at which that position changed was how fast our particle was moving, or its velocity. Now, velocity and speed are very similar, and we'll talk about how they're similar versus different in a minute. But we just discovered that the rate of change of position is velocity. How quickly you change position is how fast you're going. The idea that you should definitely write down is that velocity is the rate of change of position. The rate of change, as we know, is the derivative. So velocity is the derivative of position. That is a huge idea, and we are going to explore it more in depth. In example 1, we're going to talk about a common mathematical calculus physics problem where there is a change in height, like if you throw a baseball or throw something straight up into the air. So in this case, we have a dynamite blast propelling a heavy rock straight up with a launch velocity of 160 feet per second. Then our height, or position function, is given. It reaches a height of s equals 160t minus 16t squared feet after t seconds. So this is giving us a position function because it gives us the position of the rock in the air, since that's its height, after t seconds. Now, you can do this all algebraically, and I'm getting a lot of this from your book where they do algebra to find all of this. However, what we can do is just take a look at the graph and explore it more visually. Now, please note, this is not what the rock looks like in the air. The rock is blasting straight up. Rather, this is giving us its height over time. So this is the height of the rock, and this is the time in seconds. We want to see how high the rock goes. So we can clearly see that the highest point is up here. And if you want to find what that exact point is, you can just click it and it will tell you. So we need to make sure that we don't answer 5. Remember that the x-coordinate, or the t, is 5, and that stands for seconds. So at 5 seconds, our rock is 400 feet in the air. So our rock goes 400 feet in the air, and it does so at 5 seconds. In part B, we're asked to find the average velocity of the rock over the first 2 seconds. Now, average versus instantaneous is something we've already talked about. Average is not really a calculus idea. It's a pre-calculus idea, more like an Algebra 1 idea. And we've already discovered that velocity is the change in position. So in order to find the average velocity, we need to figure out the change in position over the first 2 seconds. In order to find this change, we can again look at the graph. In order to find the change over the first 2 seconds, we want to take a look at where our rock started and where it ended up at second 2. We have 2 coordinate points here. The way that we can figure those out is this one's pretty easy. It's 0, 0. You could also plug 0 into your function. And this one is 2 something. Now you can use Desmos to find that out, but I'm going to just do a little bit of algebra in that case. So we'll have to figure out what the y value is here. And then in order to find the average velocity, or the average rate of change here of the position, we're just finding the slope between those 2 points, which is the slope of this secant line. Remember the slope of a secant line is where it touches the function 2 times. The slope of the secant line is the average rate of change between those 2 points. It's different than the velocity at exactly 1 point, which is instantaneous. That's a derivative, and that is calculus. In this case, we're just doing the good old-fashioned slope formula. All right, our change in position is going to be the position, which is this function here, at 2, minus the position at 0. Those are our 2 y values. Remember, we didn't know this y value. We knew this one was 0 because it was at the origin. Our change in time, the time is over the first 2 seconds, so that is 2 minus 0. In order to find s of 2, you need to plug 2 into this function up here. I'm going to do that in real time on my calculator, so I'll have 160 times 2 minus 16 times 2 squared, which is 4. And that gives us 256. If you didn't look at your graph, you just plug 0 into the function. We get 0 minus 0, so that's 0. All over 2 minus 0. So that's 256 divided by 2, which is 128. Now, because this is velocity, in order to label it, we have to make sure that we're using the correct units. Velocity is the change in position. Position is measured in feet, divided by the change in time measured in seconds. Seconds should be just S, not SEC, but a lot of books and graphs will label seconds as SEC, but you can just use S for seconds. Now, part C is getting into calculus. It's asking us for the velocity at an exact time. That's the slope of the tangent line at one point. That is the instantaneous rate of change of position. Therefore, we need to do some calculus. Now, please note I actually changed part C to say at t equals 1 and then at t equals 8. I changed it from t equals 2 to t equals 1. So just in case you wrote that down at the start, I did change that there. The reason I did that is because I want to see if the instantaneous velocity at the first second is close to the average velocity over the first 2 seconds. The first second, or second 1, is squeezed in between seconds 0 and 2. So let's see how that fares out. Let's see what happens. In order to find the equation for the instantaneous velocity, we need to take the derivative of the position function. So the velocity function, v of t, is the first derivative of the position function. Remember, that was the first thing we wrote down, is that velocity is the derivative of position. So in order to take the derivative of s of t, which is up here, we're going to use the power rule. The derivative of this first term is 160. Then in the second term, we'll bring the 2 out front and multiply it by that minus 16. And then t is raised to the first here. So that is our velocity function. So v of t, our velocity function, is 160 minus 32t. What we want to first do is find the velocity, or the instantaneous velocity, just because it doesn't say average here. So if it just says velocity, it means instantaneous. We want to find that at t is 1. So the velocity at exactly 1 second is plugging in 1 to our velocity function. So it's 160 minus 32. And crazy enough, that ends up equaling 128. And then if we label it, it should be feet per second, since it is how the position of feet changes over time, seconds. That's really cool. We just found, and this is not always the case, but we just found, because it's a nice parabola that is symmetric, we found that the average rate of change from seconds 0 to 2 is the same as the instantaneous rate of change of what was right in between them, the first second. Let's see what the instantaneous rate of change of position is. Let's see what the velocity is at 8 seconds. That means we have to plug in 8 to our velocity function. So when we plug in 8, we'll have 160 minus 32 times 8. And that equals negative 96 feet per second. Looking back at the graph of the position, or the height of the rock over time, we can see that at 1 second, our function, our height rather, is increasing. Therefore, its derivative, velocity, is positive, and it was positive 128 there. So if we were to draw a tangent line at exactly when time equals 1 second, it would have a slope of positive 128, which means that the rock is traveling at 128 feet per second there. At 8 seconds, the height is changing, but it's decreasing over here. That means that its rate of change is negative. The velocity of the rock is negative here. It is falling back down towards the ground. If we were to draw a tangent line here at t equals 8, its slope would be negative 96. The last thing that we'll talk about here is acceleration, our last key idea. Now, we found that the velocity of our rock was 160 minus 32t. In order to find the acceleration, we need to find out how the velocity is changing. In order to find acceleration, we need to find the rate of change of velocity, or the derivative of velocity. So the acceleration of our rock for any time t is the first derivative of velocity. Taking the derivative of velocity, the derivative of 160 is 0, and the derivative of negative 32t is negative 32. Now, how do we label acceleration? A of t is just a constant here. It's negative 32. Well, we know that velocity in this case was feet per second. What does that mean acceleration is? It's how velocity is changing over time. So that means it's how velocity, feet per second, is changing per second. That's weird. The way that we can say this right here, or rewrite it, is feet per second squared, or feet per second per second. So the acceleration of our rock is constant. It's negative 32 feet per second squared. These are the main ideas that we have learned today. We see that position can be written really as any function. A lot of times it is written as s or x of t. We use t in these cases because we are talking almost exclusively over time. So t is used in place of x as our independent variable. Velocity is v of t, and it is our rate of change or first derivative of position. We've explored that in this video quite a bit. Then acceleration we took a look at last. Acceleration is how velocity changes. Acceleration is the first derivative of velocity. Then acceleration is also the second derivative of position. We're traveling along to the right, s of t, s prime of t, s double prime of t. As we move to the right, we're taking derivatives. So acceleration is not only the derivative of velocity, it's also the second derivative of position. The last main idea that I forgot to talk about and would like to just put over here has to do with velocity as well. It's the relationship between speed and velocity. Velocity is simply speed with a direction. That's why velocity can be positive or negative. That's a common physics idea that you probably have already learned. In order to transfer between speed and velocity, all we need to do is take the absolute value of velocity. Speed is always positive. So speed equals the absolute value of velocity. So regardless of which way you're moving, left or right, or up or down, velocity could be positive or negative. But if you just want to say the speed, you would just say the positive version of velocity. Speed is always positive, just like I hope your mindset is after watching this video. All right, take care.